So stress. And what I'm going to do here is purely, I'm going to make a heuristic argument. What I mean by that is that what I'm going to do here will not hold up in the court of mathematics. Okay, right? I'm going to get a little bit screwy with the math here, but I'm going to make a heuristic argument to talk about what stress is, because we're taught as undergraduates that like stress is this really fundamental thing, and especially it's abused in geomechanics, right? Because you talk about everything at reservoir depths in terms of stress, right? But remember that when we measure stress in geomechanics, right? If we measure stress at depth, it's typically if you've had reservoir geomechanics, you know that it's typically from some mini frac type experiment, right? You create a little fracture, and you infer that when the fracture closes, when the pressure in the fracture drops such that the fracture closes, that's what the overburden stress is, right? But that's really equilibrium, right? What you're saying is that's an equilibrium argument. You're saying that the pressure inside the fracture is equal to something, right? Well, stress. In continuum mechanics, we get stress from some constitutive law, the simplest being elasticity or Hooke's law, right? And that comes from strain, which strain is well defined as a fundamental concept, right? We just did it. We can track line segments and define strain, right? And it's strain that brings about stress, okay? So I just want to make a little bit heuristic argument from kind of physics 101 about what stress is, okay? And so from kind of physics 101, you have that an increment of work, right, is equal to some force over some distance, right? Where here this x is sort of our current x, right? So it's x, it's a function of big X in time. This is our current configuration. So the first thing I'm going to do is I'm going to divide both sides of the equation by dt so that I have like a power. So now I have that this is like a power, okay? And of course, this is velocity, right? Now I'm going to multiply both sides of the equation by what?
Do we assume that force is not dependent on time?
It doesn't matter. I mean, I'm not. This integral is over distance, right? So you'll see it won't matter. You can say it is or it's not. I'm not taking the derivative. I'm just dividing by dt, right? I'm not saying d dt of both sides. I'm dividing by dt, right? I see, if I was taking d dt of both sides, then you'd have to use the chain rule, right? But I'm not doing that. I'm dividing by dt, okay? So now I'm going to multiply both sides of the equations by 1, right? So 1 here, 1 here, okay? It's just on the right-hand side, my 1 is going to look funny. It's going to be dv over dv, right? Where v is a volume, okay? Now, you might think that dv, or you might be able to express dv as a function of area times dx, okay? But dx is clearly a vector, and this is where sort of the heuristics come in. The volume dv, it's a scalar, right? It's a volume, a little infinitesimal volume, right? But dx is a vector, Therefore, my areas, I mean, this equation doesn't make sense unless my areas are sort of like a vector, right? So this is sort of where the heuristics come in. So really, I have j areas times j distances. So it's sort of the cross-sectional area. The j's go from 1 to 3. So it's like 3 areas times 3 distances, right? So the 3 cross-sectional areas times 3 distances. Okay. This is where sort of the heuristics come in, okay? So I'm going to substitute this in to the denominator, and the denominator only of this equation. And if I do that, then I get the integral of fi, and switch to initial notation, fi aj dvi dxj dv. Well, we have a name for this. I have a name for that, right? Velocity gradient. We don't have a name for this yet, but I'm going to use a symbol. Okay. Now we can take L, any matrix you can separate into the symmetric part and the anti-symmetric part, or the skew symmetric part. And that's equal to 1/2 L transpose plus L plus 1/2 L minus L transpose, right? Well, we have a name for this. It's a rate of deformation. And we don't have a name for this, but it turns out it's called the skew. The spin. It's called the spin, or the vorticity. Okay. And so it doesn't really matter for what I'm going to do next. But so if I substitute in d plus w for L into this equation, I have where this little colon symbol, you probably haven't seen it before, it's equivalent to the double contraction of 2 tensors. So using our Einstein's notation, we have that any repeated indice is a summation, right? So this double colon indicates that we're going to sum over both indices in order like that. Okay? So one last thing, if we can show if this sigma is a symmetric tensor, okay? If it's a symmetric tensor, then any symmetric tensor times a skew symmetric tensor, which is W, it's always that double the double contraction is always 0. You can prove that. All right. So then, if we just assume that sigma is symmetric, that reduces our final equation down to this guy. Okay? So, of course, we're going to define it. We're going to define it. Not so it'll be well defined by the end of the next lecture. But of course, this sigma is the stress. Specifically, it's the Cauchy stress because it's a symmetric. And so you can kind of see that, like the F's, right? The F's are forces in the current configuration, and the A's are areas in the current configuration. It's just we're doing this over a volume, so there's, it's a vector. There's three components of the vector f, and there's three areas, or three areas defined by three normal vectors, right? And so that's where you get Fij as a tensor signal, okay? And so the point of this is that the stress, what we know is the stress, is really just something that's called work conjugate or energy conjugate, or in this case, to be very specific, since we did everything in terms of power, it's power conjugate. Okay? So the stress is power conjugate to, or in this case, to the rate of deformation or the strain. Okay? So in other words, power, work, these are thermodynamic quantities that are well defined. Okay? Strain is well defined. It's the stress is the thing that you multiply by the strain or contract with the strain, and it gives you power. Or energy or power, depending on if you're talking about strain or strain rate. Okay? So we'll see later, like we have now well-defined strains and strain rates. Lagrangian strain, Eulerian strain, right? All of those have to equal energy when you contract it with something. And because all of those are different, the stress that you contract it with has to be different. And later we'll see that there are. I mean, there's something, what we talked about here is called the Cauchy stress. The Cauchy stress relates forces in the current configuration to areas in the current configuration. Okay, but there's also something called the first Piola-Kirchhoff stress, which relates forces in the current configuration to areas in the reference configuration. And then there's also something called the second Piola-Kirchhoff stress that relates forces in the current configuration to areas in the current. I'm sorry. The second Piola-Kirchhoff stress relates forces in the reference configuration to areas in the reference configuration. All right. So I know this is all new to you because you thought up until today there was just one stress. Right? But every valid strain measure has its own work conjugate stress. Right? They're all different, and they all have slightly different meanings.